Good afternoon, everyone. My name is Ed McMahon. I'm the CEO of Epic Engineered Technologies. And thank you for attending our user interface design guidance for RTCA and DO 160 webinar. Before we get started, I just wanted to let you know that you'll be muted during the presentation. So if you have any questions as we move along, please enter them into the questions panel located in the webinar control panel. We will try to get to them at the end of the presentation. Also, we're going to be recording this webinar and posting it on the post the recording and the slides of this on our website and YouTube channel for anyone to take copies of later to share with whoever you'd like. So today our presenter is Steve Goodman. He's our user interface and cable assembly product manager here at Epic. Steve is a mechanical engineer with a bachelor's and an MBA, both from Northeastern University. Prior to being here at Epic, he had extensive experience as a product manager in the aerospace industries for two different companies, working for first-class manufacturing locations of interconnects, cables, wire harnesses, rack-mounted equipment, and board-level components. Today, in his role at Epic, he's overseeing the design, the development, NPI processes, and production of user interfaces for lots of different applications, including some high-reliability medical devices, automotive controls, aerospace, and some high-technology industrial stuff. And these applications not only included the design and the build of the hardware, but also included the firmware and software to control the operation of the device, along with all the certifications, including some product that had to meet the specification that he's talking about today. So with that, I'll turn it over to Steve, and you take it from here.
Thank you, Ed. Good afternoon, everyone, and thank you for joining our webinar. My name is Steve Goodman. I'm the product manager here at Epic for our user interface and cable product lines. The goal today is to provide some design guidance for DO 160. Our agenda, the first thing we'll be touching on are key considerations before you start testing. Next, we'll touch on some of the dynamic and environmental tests, as well as the EMI and EMC tests within DO 160. Lastly, we'll wrap all that up in a summary. So first, what is RTCA-DO 160? As many of you know, DO 160 is a standardized way of defining the conditions and test procedures in order to qualify a product for use on a fixed wing or rotary wing aircraft. There's previous revisions of DO 160 that started in the 1970s. The current revision is revision G. We're expecting a new revision to roll out in the next year. Big takeaway from this slide is that most of the requirements in DO 160 are derived from MIL Standard 810 and MIL Standard 461, and those are environmental and EMI test requirements specific to the mil-aero industry. So, some key considerations before you start testing. First, you must understand who will be obtaining the FAA certification. Is this going to be you? Will this be your customer? This must be addressed since it has a tremendous ripple effect on how you test the products, how you certify them, how you power them, how you fixture them, etc. Secondly, you need to understand, will your unit be tested as a standalone unit, or will it be installed into a next higher assembly? The reason that that's important is because it may impact the test method, may impact fixturing, how you power the unit, how you operate the unit, etc. Another key consideration is the sequence of environmental tests to be done. So for example, if you have 10 tests that you must perform, you don't necessarily need 10 dedicated units to go through each test. As you people know, some of these units may be expensive, and if you can do multiple tests on one unit, that obviously helps. The key here is that some of the tests like sand and dust, salt fog, fluids susceptibility, all of these can damage the unit, create some kind of residual buildup, and negatively impact the test later down the line. So it's really important to understand how many units you're going to set into motion for your test project, and so on. We touched on it a bit earlier in the slide, but really it must be understood how you're going to power and operate the unit. Later in the webinar, we'll be touching on the explosive atmosphere tests. That's one of the most important ones to understand how you're going to power and operate the unit. Lastly, you need to have a clear definition of what the true pass-fail criteria are. A direct quote from DO 160 says, "You must determine compliance with applicable equipment performance standards." Essentially, it's up to the manufacturer or end customer to help define what constitutes a pass or fail. And later in this webinar, you will see, for example, with the waterproofness test, ingress of water doesn't necessarily mean you will fail. So it's very important to understand what the true pass-fail criteria is. So all of these together, why are these important? Two big takeaways for me. One, DO 160 typically occurs at the end of an already compressed and stressful development life cycle. So when you may have originally budgeted 3 months to do your DO 160 testing, now you have 6 weeks. Secondly, testing's not cheap. For example, using one of the high-energy shaker tables at one of the local test labs, that can run from $2,000 to $3,000 a day, whether you're actually using the shaker table or not. So it's very important to get all of the test setup, operating, and pass-fail criteria information addressed as soon as possible. Okay, this webinar is going to cover the sections on this slide here that range from the environmental and temp variation tests all the way to a handful of the EMI and EMC tests here. As many of you know, each of these has potential issues with test setup, how you're going to design your part to make sure you actually meet the requirements, how you operate the unit, etc. So the first one we're going to focus in on are the dynamic tests, Section 7 and Section 8. Section 7 is shock and crash safety. The shock tests are typically performed on some kind of drop tower or shaker table. Shock pulses can range from 11 milliseconds to 20 milliseconds. The longer the pulse duration, the more energy, the more severe the test. For the sustained acceleration test, that's typically done on a centrifuge. It can also be done using some kind of inertial loading machine if you are unable to mount your unit in a centrifuge. In regards to our vibration tests here, the 3 main classes here are your sine vibration, your random vibration, and sine on random, which simulates the ride of a helicopter. The lower right-hand portion of the screen shows, where my cursor is, shows a random vibration floor profile with 4 discrete sine tones that simulate the different blade pass frequencies. This is very important since you may be able to survive the floor random vibration input levels, but if your natural frequency coincides with one of those sine tones, you're going to have a lot of issues passing that test. The way that the test engineers do the test is they use accelerometers and mount them at various places on the fixtures and on the unit under test to understand how your unit's behaving under test. You can measure transmissibility, essentially the amplification or attenuation of the input vibration signal. A quick way to compare one profile to another is to look at the total area under the curve, again where my cursor is in the lower right here. So you can look at 2 profiles and understand the total amount of energy or the total severity of the test simply by looking at the total area in the curve. A major takeaway for us is that fixed wing vibe is not the same as helicopter vibe. Helicopter vibe typically has lower frequency, higher G levels at those low frequencies. So if you have a part and it's currently qualified for a 737, you're not going to have a lot of you're going to have a lot of issues passing vibe tests for a UH-60, for example. So as anyone who has witnessed a vibe test knows, it's a severe, loud test. There's lots of things that can happen. Parts can loosen, parts can break. There's multiple failure modes. Really, the biggest key, if you have witnessed one of these tests, is units tend to break, bend, fasteners will back off, etc. There's lots of things that can be done to safeguard your product against these severe dynamic conditions. The most important thing to focus on is really the material selection. Make sure you're selecting the right material with the design features, working to eliminate stress concentrations. Another major thing to look at is what the system natural frequency is. And if you all remember from physics class, natural frequency, omega naught, is the square root of k over m. So if you want to shift the natural frequency of the system, you either need to change the stiffness or change its mass. So these are some things you can look at to improve your chances of passing this test. Now, if your part is designed in SolidWorks or CATIA, some of those software packages include modeling and FEA capabilities, so you can actually go and predict how a system will perform before you go through testing. That's an excellent tool for preliminary sizing. However, as many of you know, the best way to make sure you're going to pass the test is to actually do some kind of shock or vibe testing in advance. Now we're going to touch on some of the environmental tests. First one here is altitude. So this test can range from an actually 15,000 foot below sea level overpressure condition all the way to 70,000 feet in altitude. This test can be performed at temperature, whether it's a high or a low temperature. This test creates lots of issues when you have sealed compartments and elastomeric members. Keypads can balloon, diaphragms can rupture. If products aren't properly vented or reinforced, any elastomeric parts that require motion are going to have issues. So in terms of design guidance, the first thing we look at is really how to modify the existing elastomeric structure to prevent the pressure delta from impacting the performance of the system. There's lots of ways you can address this, but really it comes down to figuring out a way to stiffen or strengthen the area involved, or possibly even vent the keypad to another area and prevent ballooning. Next tests we're going to talk about are the suite of temp, humidity, and temp variation tests. So, as many of you know, extreme swings in temperature can create condensation, can create high stresses, and functionality issues with dissimilar materials. If you have two materials with different coefficients of thermal expansion, you may have tolerance issues, motion issues, etc. When it comes to safeguarding against this in the design process, the biggest key is to really focus in on materials and components that are designed for the appropriate temp conditions. If you have a known operating and storage temperature range, it's absolutely critical to have that information and select products and materials that can meet those requirements. If it turns out that condensation is an issue, that becomes less of a temperature concern and more of a waterproofness or water pooling concern. Drain ports, vents, grooves, etc., they all can be incorporated in the design to help mitigate any pooling from condensation. Takeaway from this is that operating temperatures are less severe than storage temperatures. So your unit may only need to operate from -20 to +55 C, but it must be able to survive storage conditions from minus 40 C all the way to plus 80 or 85 C. Explosion proofness. This was a test we touched on earlier in the webinar. But what this test essentially is you're creating a bomb. You have a sealed environment with some kind of fuel-air mixture, and the test makes certain that your unit will not create excessive heat, a spark, arcing that will then ignite that explosive air mixture. The big key for this test is you must be able to operate the unit during test. What is your definition of operating the unit? That is a good question. It can be just powering the unit on. There could be actually buttons, switches, or other features that need to be actuated and controlled. There may be some external software program that needs to run your unit to go through a acceptance test. These are all examples, but what must be considered is how you're going to actually operate the unit while in the chamber. There's a small view here that shows two arms in this chamber. Some of the units can be equipped with articulated fingers to go and actually operate switches and levers and such. In terms of design guidance, the biggest key here is really encapsulating live components and doing your best to eliminate the source of heat and sparks. Waterproofness is probably, along with sand and dust, one of the most challenging tests to pass for user interface products. This is because typically user interface products are riddled with buttons, keypads, places that water can enter and wreak havoc on the system. The tests defined in DO 160 range from a fairly benign condensing water test, which is in Cat W of Section 10, Cat Y of Section 10, all the way to a fairly heavy-duty continuous stream defined in Cat S within Section 10. So typical failure modes can range from your gasket or seal rupturing under the high-pressure water that's being sprayed at it to pooling of water in certain areas where it's not supposed to. In terms of design guidance, first thing to understand is if your unit is hermetically sealed and you've already done a helium leak snip test, you're exempt from this test. If you have not proven that you're hermetically sealed, there's lots of things we can do to go and improve the waterproofness of the product. But generally speaking, it involves some type of gasketing, elastomeric boots, different coatings and processes we can do to live components to make sure that they're not adversely impacted by waterproofness. We touched on it earlier in the webinar. Ingress into your unit does not necessarily constitute a failure. That's a big key. The next test we're describing here is the sand and dust test. Sand and dust has very similar failure modes and design guidance as the previous slide covering water tests. They're both categories of ingress protection, and I'm sure many of you are familiar with the IP ratings, IP67, IP65 of other products. It's very similar to this. What we have here is an example of a membrane switch that has failed a DO 160 blowing sand and dust test. As you can see, the contacts here have been covered by the ingress, and it's resulting in a poor contact between the dome switch and the contact pads. This view immediately below is a design solution that was recommended to fix this issue. We incorporated a perimeter gasket seal and utilized a unique adhesive process to bond the overlay to the rest of the circuit here. So similar to waterproofness, there's lots of things that can be done to safeguard against ingress protection, but really what it boils down to is figuring out how the ingress is entering the unit and implementing some type of safeguard to prevent that. The next test we're going to talk about, it's one of the more boring, I have to admit, is the salt spray test. You essentially place your unit in a humid chamber that has salt within the atmosphere, and over time, whether it be Cat S or Cat T, a corrosive compound will build up on your unit. The biggest failure mode here is your material breaking down, metals oxidizing, and your unit not performing properly due to the salt environment. For design guidance, the biggest takeaway here is if you have a properly designed part to safeguard against waterproofness and sand and dust, you'll probably be okay in terms of ingress protection. However, if there are exposed components, the most important consideration is the material selection and/or any outside processing or coatings that are necessary to prevent corrosion from any metallic parts, etc. Fungus test. It seems 9 out of 10 fungus tests can be waived or qualified through similarity or previous testing. There's tremendous amounts of data on the performance of certain compounds and their resilience to fungus. And if necessary, this test can be performed using a small coupon of whatever material is being used. Typically, the materials that are focused on are elastomers. If you have aerospace, aluminum, steel, etc., those are all exempt through the material properties themselves. The last test in our environmental group of tests here is the fluid susceptibility test. This one here covers 7 discrete fluid classes. Your unit will be subjected to some or all of these based on what it is and where it goes in the aircraft. There's 2 primary ways of doing this test. It's either with a spray or a submersion of your unit into these fluids and chemicals. Some of those tests also incorporate a bake cycle where you're subjecting your unit to a spray, baking it at temperature for a period of time, pulling it out, and repeating the process. This is important because you must understand the fluid classes you will be subjected to in order to properly design and select materials, coatings, etc. Certain elastomers behave poorly to oils, solvents, fuels, etc. So if you're selecting an elastomeric keypad and there is a requirement that it must be sprayed with a hydraulic oil or something like that, it must be considered what the material response will be to those chemicals. Next, we're going to touch on some of the EMI and EMC test conditions within DO 160. And again, that's electromagnetic interference. So the 3 sections we're going to touch on today are section 20, 21, and 25 respectively, which is RF susceptibility, RF emissions, and ESD. So the RF susceptibility test is typically performed below 400 megahertz using conducted susceptibility testing. In other words, you're somehow driving a RF signal in through a conducted path to your product. The radiated tests are typically performed above 100 megahertz and can be tested all the way to 18 gig. Those are using radiated susceptibility test antennas, and is typically either directional and tested in an anechoic chamber, or is a 360-degree test, which is performed in a reverb chamber. There's talks within the industry that over the next year, when DO 160 is rolled from Rev G, that the primary method for performing radiated susceptibility is going to go from the directional test to a worst case radiated susceptibility in a reverb chamber. This is important because units that had previously passed the directional test may no longer be able to pass the 360-degree reverb test. In terms of emissions, the goal here is to scan the frequency bandwidth and make sure that your unit is not emitting RF signals in a certain undesired frequency range. For ESD, or electrostatic discharge, this obviously simulates some kind of human contact in a dry air environment, maybe walking on carpet, something like that. But it's typically a 15,000 volt discharge. So ways we can safeguard against some of these EMI and EMC tests. This includes various types of shielding. Shielding can be in any number of ways as shown on this slide here, but it can be incorporated as an actual layer within one of the front panels or switches. You can use combination of these to create almost a Faraday cage around certain products that you're trying to shield from an ESD event. Your cables and jackets can have shielding, whether that be an overbraid, whether it be on a connector, etc. There's also passive components, ferrites, chokes, ESD diodes that can be placed in series within your circuit to actually help safeguard against some of these events. Another key consideration here is to make certain you have an effective and proper path to ground. One big key here is that if you are going and tying into a unit, that unit must have the proper resistance to go and reference ground appropriately. Conductive elastomers and conductive coatings are also used. If you have an elastomeric part, an overbraid on a cable, an overmold on a cable, those elastomers can be impregnated with a highly conductive material like silver or nickel to go and help with your shielding. Takeaway here is, as anyone who's been involved in a EMI test product and test project, EMI testing is very expensive. Shielding effectiveness is a way to test in advance of going through an RF project to do a quick assessment of how your product will behave. So, in summary, as mentioned, DO-160 is one of the last hurdles at the end of a development life cycle in order to obtain some type of airworthiness accreditation. Understanding the test conditions and understanding the requirements help obtain that certification faster, spending less money with less risk. Just because you fix a failure does not mean that that fix will not impact another test in another part of the system. It's important to do a careful analysis on any changes when you go and fix a product, because that may have a ripple effect or even a negative ripple effect on other tests within the project. And lastly, we strongly recommend that development testing is done before a formal DO-160 qual so that you have the best chance of passing the test the first time. At this point, I'm going to hand it back over to Ed and Keith to discuss our products.
Thanks, Steve. He's going to look at the questions that came in and come up with a couple of answers. While he does that, just a quick 30 seconds on some of the other products that we currently manufacture. And as Steve mentioned, airworthiness and certifications such as AS9100 and our facility in Largo, Florida is Navy Flight Hardware certified. And all these products that you see here, we manufacture for the aerospace industry. Everything from custom battery packs to the smart HMIs that Steve was discussing today, cable assemblies, RF filters, and diplexers, as well as printed circuit boards. So having not only the experience in smart human-machine interfaces, we have experience all across the board, not only in just building the products, but in making sure that the certifications are met so that your designs get approved quickly and into service. So with that, I'll turn it back over to Steve, and he can kind of answer some of the questions that you folks had sent in.
Thank you, Ed. As Ed said, if you have any questions, go ahead and enter them in now, but we have a few here. First one, we need to pass a DO 160 altitude test at 10,000 feet. How can you add a vent hole to a keypad without violating the IP rating or ability to survive wind-driven rain? It's a good question. Well, first, you need to make sure that the assembly that the keypad mounts to is adequately sealed and was designed with sufficient ingress protection. Once that's been addressed, next thing to consider would be to look at the volume of air trapped inside the keypad and compare that to the volume of air in the adjacent compartment. And then if possible, you may be able to add maybe 100 thou or so vent hole between the two compartments. That would then allow pressure to equalize, and hopefully the keypad should be able to function as intended. Another question here is, can ABS used instead of aluminum in faceplates and bezels? Yes, absolutely it can. ABS is a great thermoplastic, but it has some drawbacks. It can be susceptible to UV and certain solvents, but assuming that that bezel is non-load bearing and it's mounted sufficiently so that it won't go into resonance during vibe, it's definitely worth considering that as a material instead of like a 6061 aluminum, which is what I'm assuming. Another question here is, we're trying to pass an ESD test. We have an aluminum chassis that needs to also serve as a path to ground. What coatings can you recommend that will allow us to pass salt spray while still helping improve our ESD test results? There's a bunch of ways to answer that question, but a prime and paint operation is probably the best resilience to the elements. It's also probably one of the more expensive, but if you need that structure to serve as a path to ground, you'll need to mask an area and add some kind of grounding tab. That masked region that you're adding the grounding tab to should have a chem film processed in that area. Chem film would be a mil DTL 5541. We'd recommend class 3 there since it's a conductive class. Class 1A is obviously best for corrosion, but won't give you the electrical properties you need. So if your application will allow, and you can also eliminate the prime and paint operation and just apply chem film per class 3 to the entire aluminum structure. So that is all we have time for questions. And I want to thank you all for participating in our webinar, and have a great afternoon. Thank you.